we're up to a torque review. So torque is the rotational equivalent of a force. I do want to kind of cover that. That is an important thing to remember, but it involves a cross product, which does make it harder for us to work with. So what is torque? Well, we usually use the symbol lowercase tau. It is a vector, and it would be equal to r cross f. Now let's define some of this. R is the distance. Well, it's actually the vector from the center of rotation to the point of application of the force. Okay, let's kind of try and draw a situation and label things here. And I should definitely be warning you right now that when you are doing torque, you do have to identify the center of rotation for yourself. So center of rotation is your choice. Now, usually there's an obvious place where we put it, and you'll see that as we go, but you have to make that choice because you have to measure your r vector and in fact draw your r vector from that point to the force. All right, so let's imagine for ourselves here a situation. How about we make this a nice dark color? We've got, I do want the center to be filled in. That'll do. We've got a knob or something and we want to turn it, but it's being fussy. So we're going to get a nice long, I can't put it at an angle. Okay, I'll have to free draw it. We're going to put a nice long lever on it. So we're going to stick this lever that will come out. And we'll close that off on each end. And we'll see how hard it is to make this work. Pretty close, pretty close. There we go. Now we've got our lever. To this lever, we're going to apply a force. And just realizing something, I want to move this. All right, we're going to apply a force, but we're going to apply the force at a funny angle so as to make a point. So here is our force. Where is the center of rotation? Well, if we're trying to make this go around, our center of rotation will be right at the geometric center. So there is our center of rotation. And that means when we draw our r vector, it will come out directly from that point to the point where the force vector is being applied. All right, if we go back up to this, you notice that we have r cross f. Well, r cross f, we can find the magnitude and direction of it in a few different ways. Let's say we just want the magnitude. Then there's a shorthand way of doing the cross product. It would be the magnitude of our distance vector, the magnitude of our force vector, and sine of angle phi. Angle phi is technically this outside angle, although if you know anything about supplements and complements and how they behave with the sine function, you also realize that this is basically going to give you the same answer, the inside or the outside. I'm going to back that out because I don't want to talk about that too much right at the moment. All right, so r cross f, this gives you the magnitude. What gives you the direction? You can get the direction from the right-hand rule, and I'll have to write this out. Put your fingers of your right hand along the r vector. Then curl them the shortest way you can towards the force vector. Okay, so in this case we'd have our hand coming out and curling around. Notice my thumb is pointed at me. And that's the last bit we need for this. If thumb points towards you, then it's in the positive z hat direction. If thumb points away or into paper, then minus z hat. Now we're always going to drop the hat in this physics class we're doing right now, in this part we're doing right now. I'm not going to be able to use this video for review once the 1B class goes away, I'm realizing. But as long as we're in the physics 1B class, all we need to know is it plus or is it minus? That's what we're going to need to get out of it. This whole sine phi thing, I want to talk about another idea. We can, in fact, whoopsies, split the force up. So if you think about how this works, we're essentially splitting the force into an F perpendicular and an F parallel. That's one way you can think about it. And when you do that, the force, or the torque rather, the magnitude of it becomes equal to the magnitude of the r vector, the magnitude of your force vector, actually not force vector, and then the perpendicular component of your force vector. There is yet another way we can think about it, as confusing as this is. We can also look at splitting up our r vector. We'll get a perpendicular component of r and we'll get a sort of parallel component of r. And you can also write the torque in terms of its size as the perpendicular component of the r vector times the entire size, the entire magnitude of the force vector. All of these give us what we're going for. Okay, some other things we need to talk about related to this. There is a Newton's second law for torques. Newton's second law for torque says that the sum of all the torques acting on the object will be equal to I, its moment of inertia, times alpha, its angular acceleration. So let me get some definitions out there. I is moment of inertia about the pivot point. That matters. It matters that it's about the pivot point and not necessarily about the center of mass. Be careful with that. We'll maybe have another video coming up soon talking about moments of inertia and how to deal with them, because you do need to know how to take a moment of inertia from a center of mass moment of inertia to a non-center of mass moment. This involves the parallel axis theorem. All right. Alpha is the angular acceleration. So the sum of torques will be equal to I times alpha. I is acting like a mass. It's sort of a resistance to being set in motion. Alpha is, of course, the acceleration of the system. Now, the reason why we need this review and why I need to mention it is the sum of all torques. There are going to be cases we'll deal with where you have an object that consists of a couple smaller objects. You can actually find the torque on object 1, the torque on object 2, and then the sum of those two torques would be equal to the total moment of inertia times alpha for the entire shape. So it is important to us to remember that we can use individual torques on individual pieces and add them all up. It actually ends up giving the answer much more easily than trying to find some center of mass distance stuff, try to figure out how the forces relate to that, try to figure out how the moment of inertia relates to that. This just leaves us having to find the total moment of inertia and think about the torque acting on each piece. Okay, that's, I think, everything I wanted to say for review about torque. Torque is kind of a tricky concept. Hopefully I'll have a couple quick practice problems for you to look at that relate to it. We are going to have another quick video on moment of inertia coming up, so keep your eyes peeled for that coming out. And I think that's it. I hope that's it. If you have any questions about torque, ask me, because I'll base re-recording this video on what questions I get asked. Okay.